So yeah, welcome to session 7. Today we're going to be hearing from Nanak Nihal, who is the CTO at Holonym. And he's going to be talking to us today about ZK programming using Circom. So thanks for joining us today.
Thanks so much for having me, and thanks for interest, Sarah. Let's dive in. Just gonna pull up my screen. Cool. So, how do we write circuits in Circom? Why would you want to write circuits in Circom? So, I'm going to start with a quick summary of why you might want to or might not, why you might want to or might not want to write circuits in Circom. So then we will. Sorry, I don't know how to mute this phone call. Is this me?
Yeah, we can see your screen.
Okay, cool. I think, yeah, I was getting a phone call. I don't know if it annoys everybody else, but okay. So yeah, I'll start with a summary of why you might want to or might not want to write a circuit in Circom and the differences in writing ZK circuits versus writing regular programs. We'll start with some basic examples of syntax and concepts for writing ZK circuits. And then we'll end with some more high-level ideas and simple apps and protocols and use cases. And we'll talk about like next steps and primitives that might be helpful for certain use cases. So let's first talk about like what are the strengths and weaknesses of Circom. So what's good about it is one, it's super efficient because it's really low level. It's really close to the actual circuit level. You're pretty much handwriting gates. And what do I mean by gates in the Circom? Just like regular program is going to have and not and XOR gates. In these type of ZK circuits is a bit different. They're addition and multiplication gates. And so in Circom, you can get pretty close to that super low level of the gates themselves. And everything is very well optimized. You can think of it as the equivalent of assembly for ZK. It's one step above machine code in writing in binary, but it's not too many fancy abstractions to make life easier. So this is going to make it very efficient, and it's going to help you think of writing in a way that's really a ZK way, not like a regular programming way. It'll help you think of these as circuits rather than as programs. The other really great thing about Circom is that there are lots of libraries out there, lots of open source tools that you can use with Circom. It's been around a really long time. It has that lindiness. And so if you're looking for, let's say, AES, you'll find that in Circom. You might find that in other languages, but other stuff you will almost definitely only find in Circom. Either way, we're kind of in the very early days of ZK programming, so a lot of stuff there just are not circuits for or libraries, but most of them, they will be in Circom. So that being said, there are some limitations of Circom. As I said, it's very low level, so it's not the easiest developer experience. And because you're thinking of this in terms of like a new programming language, and more than that, just a new paradigm for writing code, that doesn't have to, you're not executing instructions on a process. I mean, you are, but like that's not how you should think of it. It's more writing constraints in a circuit. It's a new learning curve, and so it's just hard and sometimes slow because there are not as many fancy abstractions. So what are these like differences between circuit programming and regular programming? Well, one, you don't really have functions. and you focus on what are called constraints. So Circom has syntax that's a bit like functions. They call it templates. We're taking some code that makes these certain constraints. And by the way, by constraints, what is meant, I think I glossed over that, is the whole goal of a zk program, which is not really a program, but I should say zk circuit. The whole goal is to check that certain things are true, that you have these algebraic relations between certain variables. That's all it can really do. It can check you have a witness that satisfies these constraints. So your witness could be a execution trace of your program. You're adding these numbers, multiplying them. Eventually, you have all this complex logic that will, maybe take the hash of somebody's name and date of birth and prove some stuff about it. Ultimately, all these, can be expressed in a series of algebraic relationships between inputs, where you're either adding inputs or multiplying them together. And that's all we mean by constraints. That's all running this really is about. It's not about getting the output. It's about proving these relations between the input. So it's really core, this concept of a constraint. And in Circom, we'll see this operator a lot. It's like a triple equal sign. There's also double equal sign with one of the angle alligator brackets next to it. These operators are constraining. You can think of it a lot like an assert statement, though. The other huge difference is that fundamental unit of information we're used to in computing is a bit, either 0 or 1. And so usually we're working mod 2. You can have 0 and 1. You add 1 plus 1, you get 0. You add 0 plus 0, you get 0. You add 0 plus 1, you get 1. We're all working mod 2. So every number wraps around mod 2. It wraps around 2. Whereas in a zk circuit, you're usually working with a large prime number. Now, there are exceptions, but I think for anything you're writing with Circom, you'll probably be working with a large prime, which is usually this prime number, this very large thing. And that's the smallest unit of information. So if you're just trying to represent something that's 3 bits, well, unfortunately, you're going to take a lot more than 3 bits to represent it, because everything has to be represented by this 254-bit prime number. So to give a code example of how this works, to see the wraparound, here's a Circom template. You can think of it a little bit like a function, but it's not quite a function, as you can see. And what we're doing is, this is this large prime, the 218 number. We're taking an input signal that the user provides, and we're adding it to this modulus, and we're constraining that the output is X itself, right? And this is because of the wraparound. You can see that it does make sense to constrain X to itself plus this number, because we're working modulo this number. It's going to wrap around after this number and eventually just be X itself. So the next important concept with zk programming that you don't exactly have normally is public inputs and outputs. So if you're using zk for privacy, then this matters. So usually in Circom, every input is private by default. Outputs are private by default, unless the template they're output for is the main template or the main component. Circom calls things templates that look like this, and then there's a way of making like a main one, so that when you run quote unquote a circuit, it's going to treat that as an entry point. So it's an entry point main component, then the output will be public. Otherwise, if it's some intermediary output, that's not that main one, then it's going to be it's going to be private. And so here we have an example of a main component. So we're taking the do something template. By the way, field demo and outputs demo, which I've imported on top, these are the previous ones. So this is the outputs demo. This is the fields demo. I can share the source code for afterwards. But yeah, it's essentially imported those templates, put them here within the do something template. And then we're letting the user supply 3 inputs. Field demo in, outputs demo in A, and outputs demo in B. We're just piping these to the fields and outputs templates. You can see we're calling component field demo equals fields, component output demo equals outputs. That's just instantiating, so to speak, those templates. And we're constraining the input of field demo called X, and as field demo in, we're constraining the outputs demo inputs to the user inputs here. And then we are constraining our output signal of this template to the outputs demo C, which is the output there, right? So we're constraining all these things. And then on the bottom, we have 2 ways of declaring the main component. The first one is without any fancy syntax. They're just component main equals do something at the end. And this only reveals the output that was declared as output. But if we want to also reveal some of the inputs, then we can add the syntax at the bottom showing that we want to make field demo in and outputs demo in A also public. So if you'd like to follow along, we can start with like a simple example of constraining that the user gives input hello world. And this will be the code for it. But first, let's walk through how to actually how to actually install Circom. So let's see. First thing you're going to do, if you don't have Rust, you're going to want to install it using this command. I'll type it in the chat. And I'm typing all these commands to the chat, so you can do them at your own pace. We actually don't need to install Snark.js for these purposes, but definitely install Rust if you don't have it, and then you'll need it to build Circom. And if you could just give like a thumbs up or some sort of reaction emoji when you're done, then I'll know not to keep you waiting too long. Oh yeah, good question. So if you just want to install it for specific repo, then I believe you can just do the -- save flag, npm install -- save. Yeah, I don't know why. I don't know why the Circom demo, the Circom doc says install globally. I think because you will be running like Snark.js as a command line utility. So I think that's why they install it globally. I'm actually not sure the one I typed will I don't know if there's a way to install Circom locally too. Because Yeah, I mean, so with a cargo install, I don't know. I think since we're installing these as like executable binaries, or at least something executable in the case of Snark.js, which is in JavaScript, um, I think we actually might have to use a global installation, but there might be some docs on it for on Circom side. Cool. So to get started, we can write a program to constrain that the user has supplied hello world as input. And I would put the code, but I think it's sometimes nice instead of copying and pasting to like be forced to type it out. I mean, up to you if you actually want to do that or not. But yeah, you could also like try to figure it out and just use this as a template. No pun intended, of how to do it. While you're working on this, I'm going to put these circuits in a public GitHub because I wrote some like demo circuits throughout this presentation, and I think it'll be easier if you have the option to copy and paste it. So yeah, I'm just going to quickly do that while you're working on this. I just realized I didn't send you the actual characters for Hello World, so I'm putting that in the chat. Although I guess that's also available online. Okay, I uploaded the code examples to GitHub. And so you'll be able to find this under helloworld.circom. I'll just pull up my screen now. Sorry for the interruption there, or for the delay. Okay, so we have the hello world constraints here. So we're just taking an input of 12 elements from the user. We are constraining it to be, the characters of hello world. That's it. We're going one by one. And here's what I mean by Circom doesn't have too many helper functions or syntactic sugar. We're just going one by one by all the elements and constraining them to be equal. So now what if we want to go a bit further and say, okay, well, that's a stupid example. Let's let the user select some private inputs now too. Okay, and we're just going to check that part of it is hello. We don't care if the next part's a world. It can be anything else. It's 5 characters. So this would be a code example for that. You can, if you like, you can try to figure it out. It's also in the repo as well, right under it, the constrain hello 5 template. So instead of going through all of them with the for loop, we're just going to go through the beginning 7. Okay, so here's where it gets a bit harder. Let's say we want to constrain the private input to be hello anything. It doesn't have to just be 5 characters. You end up running into an issue where you can't have variable length inputs. If you try to remove the 12 here or the 11, like it's going to be really it's going to give you an error because the thing is, this is a circuit, not a regular program. And this ends up being like such a pain. Like it's the biggest pain when you're writing zk circuits instead of regular programs, because if you want to deal with variable length strings, you're going to have to plan as if the circuit is for as many characters as possible. You can't have the circuit be different length for different inputs. Like when you make the circuit, there's no knowing what the input's going to be. There are no conditional statements here. You just have to go through all possibilities. So usually the way people would do something like that is by making a sort of padding or mask. And let's say we don't care what the last 5 or the last n characters, or like we can do up to 20 characters. Then you let the user supply a mask of all zeros up to a certain point. You can, maybe prove that the mask consists of a bunch of zeros at the end. And ones at the beginning. You multiply it by that mask. So the other ones are 0, and you reveal the full thing. And then you make sure that the full thing is is hello with a bunch of zeros after. So that's how you would do it with a variable length input. It's a bit annoying, but it's unfortunately just the way zk programming works. So let's get a little bit more interesting with the example. And you'll find this in a file called, I believe, hello SHA-256 or SHA-256 hello, I think that's what it's called in the GitHub repo. Here you will constrain a private input, right? All the inputs are private by default. We're making sure that the first 5 characters are hello. And instead of revealing the rest of them, we're going to reveal a hash of them. And to do this, you'll have to run npm install Circom lib. It's a good point about remix. Yeah, so you want to install Circom lib, and then you'll be able to just include it from your node modules. You could also just you can find this on the Circom GitHub as well, the SHA-256.circom in the bit.fi. Unfortunately, the SHA-256 only takes bits. There are versions with bytes as well. You can find templates for that. And so there are a couple new syntaxes here, though, that I want to point out. So the first one is we are declaring this num to bits. If you've seen the second for loop, the first line of the second for loop, we are declaring it with a certain size. So we're using generics right here. So the num to bits component, if you look at it, it actually has a couple arguments to the template itself. In this template, this argument determines how many bits the input is. And the reason why it uses these generics, why you can't just specify this at runtime, is because these circuits are fixed length. We have to know how many bits we're dealing with because that's going to tell us how many constraints there are going to be, and we have to make all these constraints up front. So you want to choose a maximum number of bits your input might be. In our case, 8. It's not going to be more than 8 because we're dealing with bytes here. We're taking ASCII input and making it into bytes. And because there are 11 inputs, there are going to be, the SHA-256 also, you can see there are generics there. 8 times 11 bits is the size of input. So we're going through this for loop. We are instantiating this num to bits template, and we are constraining its inputs. By the way, this operator, we've seen this operator before, but I'm realizing I never said what it does. The angle bracket followed by 2 equals. This constrains and sets. So if you just do 3 equals, it only constrains these things are equal. But this one constrains and sets it. So we're gonna go through a for loop within it. You'll end up using a lot of for loops in Circom because there isn't much syntactic sugar. But it's a trade-off for getting this really good low-level access to building a circuit. We're going to constrain the inputs of the SHA-256, the outputs of the num to bits. And I should say the num to bits is just converting, these ASCII characters into bit versions. So then, we're outputting this digest. And because it's the main component, this will be publicly revealed, this output. So we've done something more in line with what we think of as a regular ZK proof. Instead of a trivial hello world example, this is still somewhat trivial, but we are actually giving like a public output saying like, hey, look, I know something. I'm proving that this digest, this output of the hash function starts with hello. I won't tell you the input, but you can tell like from this digest, you can't reverse it. It starts with hello. And why that's a little more interesting is because it's non-reversible. So when we talk about what circuits are actually useful, it's almost always going to have something non-reversible. For example, like, because if you're saying, oh, well, here's the output, I won't show you the input. If you can easily reverse the input from the output, there's no point having the inputs be ZK. So usually for a ZK circuit, you're going to want to do something that's not reversible if you care about privacy. So anything with one-way functions, I don't know why this, I chose this image. It's just It's just a default image, but it looks nice, so we'll keep it. So we'll want to prove something about a one-way function, usually. Like we want to prove that my name, date of birth, etc. hashes to the certain value that was signed by the government, and then my age is over 18, right? There's a hash in the signature. These are non-reversible. So now let's go to an actual use case. And I love this because it's super simple. It's actually like the fewest lines of code I think we've seen so far. And this does something that is somewhat useful. And there's actually a company that got acquired for essentially doing something like this, where instead of logging in with passwords, you just send a zero knowledge proof you know the password. So it adds a little bit more security in that you're not actually sending your passwords to a server, you're keeping the password always locally. And so, if somebody can intercept what the server sees, they still can't see your password. Server still has a hash of your password, hopefully with Assault, but it doesn't see it ever. So there's one new piece of syntax right here, which is with this Poseidon hash. By the way, Poseidon is a hash function. It's very, very efficient in ZK circuit. It's actually relatively slow on consumer hardware because like it's using these field elements instead of like standard bit operations. But the thing is, it can be written in very, very, very few field operations. And I'll talk a little bit more about hash functions later and when to choose one versus another. But yeah, Poseidon is nice, and you can see we're giving a generic 2, meaning we're going to want to give it 2 inputs. And these will be the password and the salt. So here's a nice, this is my favorite syntactic sugar in Circom. Circom doesn't have too many of them, but this one's really nice, I think. Instead of like having to manually constrain the inputs, this is shorthand for it. We're actually like putting another parentheses after the generics, and these constrain the inputs to be the password and salt. And so before I get to the next slide, I realized I should just touch on like, just give an overview a little bit more. This output is just going to be the output of the Poseidon hash. So essentially we've just proven we've taken an input password, and the one limitation is this password has to be a single field element in this example, this simple example. And yeah, so we're revealing the digest of it with the salt, and we can prove that our password corresponds to a particular password hash, but don't reveal the password. So I mentioned the Poseidon hash. This has become sort of the gold standard hash in ZK. If you don't know which hash to use and you have a choice, I would usually recommend using Poseidon hash. There are other options though. For example, there's the MIMC7, or maybe it's called Mimic7. I don't know how people pronounce it. It's also quite efficient in the ZK circuit. We will talk about what makes some things efficient in circuit, like other things not. The reason why something like Poseidon is super fast, but SHA-256 is relatively slow. By relatively slow, I mean about 100 times slower than something like Poseidon. Is it 100 times? Yeah, about 100 times slower than Poseidon. Is that is working in bits. Regular computers are very fast at working with bits, so doing 20,000 bit operations is actually a lot easier than doing 200 operations over this finite field modulo some large prime number. Just because that's how the hardware is built. But in our case, we're only working over those fields, so all those 20,000 bit operations end up being these huge field operations. So it's a question of like doing 20,000 field operations versus doing say 200. Yeah, so Peterson hash is not super popular, but sometimes it's used. And one thing to be wary of is that it's not, the output's not necessarily random. So you might want that from a hash function and it might not provide that. Otherwise, it's a good, efficient hash function. So other one-way functions we might want to put in a zk circuit could include symmetric encryption, such as AES. I believe there's AES circuit in Circom. I think there might also be a cha-cha poly circuit in Circom. These are relatively efficient, you know, not like super fast like with Saturn or anything, but not terrible either. You can also do asymmetric encryption. And the way I recommend is Gamal over the baby jub curve. We'll talk more about baby jub curve and why this is really important to ZK programming. And for signing, also recommend EDDSA over baby jub. So Circom has implementation of EDDSA over baby jub. So that makes it nice. I don't think Circom has implementation of Gamal, but there are at least 2 implementations I know of. One is by us, Holonym, somewhere in our GitHub. If you search for Gamal, you'll find it. And the other is PSE. That's team, I forgot which team at PSE that has done Gamal encryption over baby jub. I do recommend using these circuits because there are some checks that you could miss, which might might be easy to miss if you do Gamal. But why baby jub? So you don't need to use baby jub curve. Sometimes if we're on Ethereum and signatures are over a different curve, like SecP 256K1, then we have no choice but to use that curve. But baby jub is super, super efficient. Reason why is because in order to do the elliptic curve operations, we're not going to get into how they work, but the elliptic curve operations of a jub curve were engineered such that they only, like the numbers used for them will always be smaller than this, the modulus, this large prime number that we work in. So that way we don't have to deal with multiplying numbers that are any bigger than a field element. You can multiply and add bigger numbers than a field element in Circom, but it's just going to be, is going to be less efficient because you have to do fancy big number arithmetic. And how much less efficient? I should say more probably. I'd say also about 100 times less efficient, roughly. Maybe a little better. Maybe like, I don't know, 60 times as efficient. So let's build another practical protocol now. And this one is more a thought experiment. We're not going to write the actual code for this because it would take too much time, but we're going to design a protocol where an admin can give roles to other users. These could be in different groups. It could be in a like elevated privileges group. It can be in a view only group. It can be in a group that can view certain things, write other things. Either way, the groups just have to have some label, and we assign people a role based on which group they're in, and people can prove they're in a certain group without revealing who they are. So let's take maybe a couple minutes to think about this, how we would design this protocol, and then we'd love to hear some ideas. Okay, so any ideas? I think that's a no. Or wait, was I on mute for that? In case I was in mute, I'll mute when I ask any ideas. Yeah, I'll ask it again. If anybody has any ideas how we could build this protocol, feel free to unmute yourself.
I think there's maybe a couple things dropped in the chat.
Yeah, and
yeah.
I also had the microphone. So yeah, if anyone wants to turn on their microphone, they can.
And yeah, so if it is like proving to have a certain access level, and yeah, I think the architecture will be somewhat similar to proving you have a password.
Right.
So the idea for this is, the initial idea, there are a couple ways to do this, actually, but one way is that each user will have a private and public key. So the private key will be a hash of their public key. Sorry, vice versa. Public key will be a hash of their private key, just as an example. And admin will sign off on their public key having a particular role. What I mean by sign off, they'll do a signature. If you recall from a couple of slides ago, there is a signature primitive that works very efficiently in zk, which is EDDSA over the baby Jeb curve. So the admin can do a signature here, and then the user, if we want to look at the actual circuit, the user, what they have to prove is just that they know a certain private key that hashes via Poseidon to the public key, and that the admin has given a signature binding the public key to the role. Maybe the admin signed this public key has this role, and then you just prove you don't reveal, you don't have to reveal anything really except maybe your public key. Yeah, you just have to reveal that you know some private inputs to a signature of your public key and your role, and the signature is really from the admin. So that's all you have to reveal actually is the admin's public key. So then the circuit proves, okay, well, here's the public key and I have something signed by it, which is my public key and my role. And yeah, you should be good to go. By the way, I've used public keys in two ways. I say the admin's public key. That's going to be a baby Jeb public key. So if you're familiar with signatures, if you're not familiar with how signatures work with like public private keys, then this wouldn't really be a very immediate solution. But if you are, then yeah, this is I think a nice way of doing it.
Yeah. So the additional part here is that there is something signed by the admin that gets as an input to the proof.
Exactly. Yeah.
Hmm.
Yeah. So it's going to require some work on the admin's part to maintain, who has these roles, has to sign people when they want a new role.
Right.
There's one big problem with this setup, which is that if the user wants to change their role, or even if the admin wants to change a user's role, the old one's still valid. So this is bad, especially if a user gets compromised. You don't want them to have the old role. So let's think of a new architecture that might fix this. I'll also pause for a minute and let everybody think about this.
Because you're almost trying to build like a revoke feature where the previous proof does not work.
Yep.
Or that sort of like the previous proof gets replaced with a new one. So the verification process really does not enables the previous proof to be verified. We implemented something like this with some sort of like a time limit where a proof only is valid until a certain time period. But maybe in this case, you probably need another input, which could act as a parameter for if that changes, then the proof is invalid or a new proof is required.
Yeah, that's a nice idea with the time. I think that practically would probably accomplish a lot of the goals of this. Now, for the sake of this exercise, it's not the solution I was thinking of, because we want to be able to revoke it anytime. But yeah, I think that would work in practice. Well, obviously it did work for you guys in practice. So
we did it basically for like KYC and stuff. So it's like if the compliance requirement is that you got to do KYC every year, so after 1 year you got to renew your KYC, so you're creating new proofs. You're renewing your proofs.
Yeah, yeah, we also do expiration for that.
Jay, so, go ahead with your solution. So
yeah. So this is definitely not the most obvious solution. So I want to give a little bit of context first for it. And this is with an accumulator. So if you're not familiar with accumulators, they succinctly represent a large set of values. So you can have a set of a lot of things, maybe every user's role that's valid right now. And then you can quickly prove that the set has one of these values. So usually if we're talking about like an array, you're going to have to iterate through all of them and show it's one of them, which can be kind of expensive in a zk circuit, especially if the array has variable length. But instead, if we use a accumulator, Merkle tree is probably the best one for this use case, and just for zk circuits in general, Merkle trees end up being a common construction to prove you're a member of a set. You can really quickly prove it. And so how Merkle tree works is it's a hash of hashes of hashes of hashes. So exponentially it grows at each level. It starts with 1, next level has 2, next level has 4. So, with just 8 levels, you get 2 to 8th leaves at the bottom, is what they're called. And with 16 levels, you have I think quite a lot. 20, I think you have over 1 million. Anyways, it grows quite quickly. It grows exponentially. So in order to prove, though, this exponential growth is important, because if you want to prove that, let's say, leaf 2 is part of this Merkle tree, all you have to do is provide the hash of leaf 2 and the hash of leaf 1. And then anybody can see that these hash to, their parent node. Then you find the sibling of the parent, the one to the bottom right of top hash, and you supply that too, and anybody can see this hash 1 with the hash 0. Hash them, you get top hash. right? So you just have to traverse up one of these branches and provide these values along your traversal path to reconstruct the top hash. Once you've reconstructed the top hash, you've proven that you have a member of the set. So now you've proven that the L2 is part of it just by giving a hash of L2 and, you know, iteratively going up the tree, hashing each thing with its neighbor. So there you've proved that one of the leaves is in the top hash using only logarithmic, you know, since it grows exponentially. You know, even this, though this has 2 to the power of 2 leaves, it you know, this is a weird example because in this case it's actually probably more efficient just you know, because the tree's so shallow. But if you have like, you know, 2 to the 8th leaves, then it only takes 8 iterations to do a Merkle proof that you have a member of the set. And this is really nice for a circuit because you can make a huge Merkle tree that stores a billion different values, and you can prove it somewhat efficiently in a circuit. And it's fixed size, but that's fine up until a billion inputs. You don't have to worry about it. So a new architecture with this in mind is that the admin can make a Merkle root of all the accounts and their roles and publish this on a blockchain. And they update the most recent Merkle root on the blockchain anytime the roles and permissions change. So the users then can do a Merkle proof that they have a role in the most recent Merkle root. And so I didn't do a code sample for a Merkle proof because that's, you know, it's a whole thing. But there is this great GitHub repo that a lot of people use for Merkle trees, and it has both the Circom and the JavaScript. And I believe this is open source. I mean, it must be. I think it's by, yeah, it's by PSE. So I'm quite sure it's open source. I mean, I think so, even though there's no license. But yeah, I mean, so you can use both the Circom files. It gets a bit complicated with the multiplexing, right? So it's not really in the scope for this, but I do suggest looking at the code for it. It's pretty interesting. And this is a super helpful primitive for lots of stuff you'll build that involves set membership in Circom. Stuff like semaphore, for example, uses Merkle trees. If you're familiar with semaphore, which is a popular way of proving set membership, this is based off of, or at least when it started. I haven't followed it recently. I know they made updates, but at least when it started, maybe now too, probably now too, it uses this, it uses a Merkle tree for set membership. Cool. So this ended up being right on time. That's great. Yeah, definitely wasn't like rehearsing it that much, but I'm glad this ended up being perfect as far as timing. Because yeah, there's the last slide. So the next steps are, you know, we've made some templates, but then how do we actually compute the witness and generate the proof? I did include that here because it's described pretty well in the Circom docs. So to make the witness, you can do, the Circom docs saying for making a proof, there are a couple ways of doing it. The nice thing about Circom is it isn't tied to a particular proving system. So at Holonym, we've actually made our own implementation of a proving system called vol-by-zk that it's not succinct. So, you know, not the best for putting on blockchains, but it's super, super, super fast. So it can be used on like mobile devices to give privacy on consumer hardware. So you can also import Circom from there if that's the route you want to go. Otherwise, Circom, and that's in this link right here. Otherwise, Circom supports Gros16 and Plonk, which are popular proving systems. Gros16 being one of the slower ones, the same with Plonk also being one of the slower ones. but these also being the most succinct ones. So different ends of the spectrum from the prover we've implemented. So being succinct is really good for putting on chain, but not as good for speed, because it's very small, so it won't take much gas. I do recommend using zkMonk as a linter. It's very, very easy to make security mistakes when you're writing ZK circuits because it's so low level and it's cryptography, and like, these tools were not exactly built with security. Not like Rust level, like, we'll try to make the language so nobody can make mistakes. Like, no, this is like closer to assembly. So yeah, definitely recommend a linter like zkMonk. And then, the next step is just building cool applications. Hopefully, like the ideas presented so far with the password and the rules gave some inspiration, but there's a whole universe of ideas out there that are just waiting to be made. I think there's lots of really cool stuff that can be made with zk and with Circom, if you want that low level performant way of doing things with lots of extensibility, and you're okay with the harder learning curve involved. So yeah, I mean, also happy to help anybody's journey with Circom. I don't have my socials in this slide. I should have added that. I'll put it in the Google chat. And yeah, please feel free to reach out to me, and happy to answer any questions now as well.
All right, thank you very much. This was really hands-on, which is really, really great. I think, yeah, we have a little bit of time for a few questions. If anyone wants to either drop in chat or unmute. I think I see one in the chat. Can you post the GitHub repo for the Merkle tree proof? So maybe we can share that as well.
Cool. Will do.
Otherwise, I guess while we're waiting for some other questions, I did have one just related kind of to what you were saying there at the end. From a development perspective, I guess, what are kind of the use cases or the advantages for choosing Circom over some other tools? Like you mentioned your Plot, Rot 16, I know there's like Socrates and other things out there. What's kind of, what would you recommend as far as like when and why to choose Circom for projects?
Yeah, I think the two big reasons to choose Circom are if you want the libraries for it. So like Circom is one of the older ones, and has probably the biggest community of any language. So you're going to get a lot of both like libraries. Let's say you want to do something like verify Ethereum SecP to V6K1 signatures. Circom has, I think, multiple implementations of this, whereas it's less likely that other languages will have something like this. I mean, I think a lot of them, there's a somewhat popular ones, a lot of them might have it, but Circom is the most practical for when you want to do these custom things that are not very standard. The other ones I think are really promising, like for example, like Noir and like Leo. So I don't know too much about these. I know Socrates, I have done some work in Socrates, and I do like Socrates a lot for the interface. It is very easy to use compared to Circom. I think Noir and some of these more modern ones like Pyro, Leo, I think they are even easier to use probably than Socrates. But they and Socrates will also be like a lot less efficient than Circom for many things. Not everything, but Circom is just very optimized. It's been around for a while. That's kind of one of the major reasons I like it.
Got it. Thank you. Anybody else? Any other questions?
I don't mean to knock on like the other ones, by the way. I think like we definitely need something better than Circom for like for like I think the average programmer who doesn't want to get this low level. But yeah, like I think yeah, definitely a huge fan of this, and there's actually been a lot of really impressive improvements in these more modern languages and even general purpose ZK VMs in becoming more and more performant and having more and more library support. So it's like, yeah, definitely on the roadmaps.
Yeah, makes sense.
Oh, and as far as Gross 16, because you asked that as well, like Gross 16 versus Plonk, something like that. So these are proving systems. And so Circom, it does come with a couple proving systems. It comes with Gross 16 and it comes with Plonk, so you can choose either of them. Our vol-based prover also works with Circom. So you can actually use Circom circuits with a couple different proving systems. I think they're also supporting like FFLonk now, and so I think there are probably like at least 3 or 4 that you can use. There's also Nova Scotia, which can let you use Nova with Circom. So yeah, you have a few options there, and yeah, I think like Noir also supports Plonk, maybe some other ones, I don't know. Yeah.
Yeah, thank you. Okay, any other questions? Going once, going twice. All right, if no one has anything, then I think we can probably wrap up for this session today. So thank you very much, Nanak. This was awesome. This was super helpful. And yeah, if anyone else has further questions, as always, you can reach out in Discord and we can get back to you. And yeah, I think that's it.
Thanks, zkMonk team, for having me, and thanks everybody for listening. Hope you got something out of it. And yeah, thank you very much.
Thanks so much.